Welcome. The topic we'll be discussing in this lecture is memory locations, addresses and operations. So basically we'll be discussing like how memories were accessed, right? Like how memory is accessed in different locations. Uh, Normally it is accessed, memories are accessed as byte, okay? And how, what is a word, what is the size of a word, how the word size varies with computers, right? And what is meant by big endian format, what is a little endian format, and what is the role of load and store operations. The typical memory operations are load and store. Load is used to read something from the memory, and store is used to store something to the memory. So how all these things works. So that's what we'll be discussing in this particular lecture. Fine. Let us start. So so what is a memory? So memory, so basically memory is a collection of locations. Okay. So memory is a collection of locations. The individual location in the memory is called as bits. The individual location in the memory is called as bits. And we group 8 bits, and the group of 8 bits is called as bytes. The group of 8 bit is called as bytes. Okay, 1024 byte is 1 kilobyte, and 1024 kilobyte is 1 megabyte, and 1024 megabyte is 1 gigabyte, right? And 1024 gigabyte is 1 terabyte. Okay, so the basic unit of memory is bit. So a memory unit may contains millions of bits. Okay, but actually we don't address at bit level, but generally we address memory at byte level. Okay, so memory consists of millions of storage cells, each of which can store one bit of information. Okay, so the basic unit of memory is called as bit, which can store one bit of information, which is either 1 or 0. Okay, and data is normally accessed in the memory as a set of what do you call as set of n bits. And if you access memory as 8 bits, then that is called as a byte. And a typical computer will have some word length. Typical computer will have word length. So if the word length of your computer is 32 bits, then the data will be accessed from the memory as set of 32 bits. Okay. If the word length of a typical computer is 16 bits, that is 2 bytes. If the word length of a computer is 2 bytes, then every access in the memory will be in terms of 2 bytes. If the word length is if the word length of a computer is 4 bytes, okay, that is 32 bits, then every access in the memory will be in terms of 4 bytes, that is 32 bits. Okay, if the word length is 64 bits, then every access will be in terms of 64 bits or 8 bytes. Okay, so this is a memory structure you can see. So how the memories are accessed, that actually depends on the word length of the computer. That actually depends on the word length of the computer. So depending on the word length, a set of n units will be accessed from the memory. Okay, so so this is how we can visualize memory. So this is the first word. So if the word size of this particular computer is n bits, if the word size of this particular computer is n bits, where n can be either 16 or 32 or 64, it depends on the type of the computer. For a given computer, if the word size is n bit, then each location will be accessed uh, as n consecutive bits. Okay, so that is when you perform one read operation, you will get all these n bits, right? So this is called as first word, this is called as second word, and this is called as ith word, and this is called as the last word. Okay. So the key takeaway point is memory is accessed in terms of words in a computer. Memory is accessed in terms of words in a computer. And what is the size of a word? The size of a word will be n bits, where n may be either 16, 32 or 64 bits, depending on the type of the computer. Okay, fine. Okay, so let us assume that a typical computer is having a word length of 32 bits. Let us take a typical computer whose word length is 32 bits. Then it will be represented like this. That is, each word will have 32 bits. So this is bit 0, bit 1, so on and so forth up to bit 31. Okay, so totally there are 32 bits starting from bit 0 to bit 31. Last bit is called as sign bit. Okay, this is called as the most significant bit, MSB. So we call this as MSB, the most significant bit, and this is called as LSB, the least significant bit. So this is LSB, the least significant bit. The most significant bit is called as the sign bit. Okay, for all positive numbers, this sign bit, that is the bit at location B31, will be 0 for all positive numbers, and it will be 1 for all negative numbers. Okay, fine. Okay, so if the computer's word size is 32 bits, then a 32-bit word computer is nothing but, it's a 32-bit word is nothing but, it contains how many bytes? 4 bytes. Okay, so this is the 0th byte, this is the first byte, this is the second byte, this is the third byte. Okay, so uh, totally it has 4 bytes, right? Totally it has 4 bytes. Okay, so each byte is nothing but an ASCII character. So each byte is nothing but an ASCII character, because the size of, what is the size of ASCII character? The size of an ASCII character is 8 bits, that is 1 byte. Okay, and totally how many ASCII characters are there? We have 2 to the power 8 ASCII characters, that is 256 ASCII characters are there. Okay, so if the word size is 32 bit, then each word will have 4 bytes, where each byte will be an ASCII character, right? ASCII characters includes everything. It includes all the alphanumeric characters. It includes alphabets, numbers, all special characters, everything. Okay, right. Okay. So to retrieve information from the memory, we need the address. Okay, we need the address. To retrieve information from the memory, or to store something into the memory, we need the address. So if a typical computer is addressed by using k bit, if a typical computer is addressed by using k bit, then it can maximum address 2 to the power k locations. Okay, if a typical computer is addressed by using k bits, for addressing, if it is using k bits, okay, or k wires, right? Okay, we have discussed about bus. We have discussed about bus, and there we have discussed that the bus contains 3 types of lines: data lines, control lines, and address lines. Okay, so in the bus, there will be some set of address lines. Okay, so if the number of address lines were k, if the number of address lines were k, then using this particular address bus, you can address 2 to the power k locations. Okay, if the number of address lines is equal to k, then using this particular address bus, we can address 2 to the power k locations. That is from location 0 to 2 to the power k minus 1, right? Right, if the number of bits available to address a bus, if the number of bits available to address a memory is k bits, okay, then using a k bit bus, using a k bit address bus, you can address 2 to the power k locations, that is from location 0 to 2 to the power k minus 1, right? Okay, right. So the point I'm trying to say is, there are k bits to address the memory. If there are k bits, if you want to send k bits, then you should have k address, then the address line also should have k lines. Okay, so if there are k such address lines, and then you can send k bits through these address lines, then using this bus you can address maximum 2 to the power k locations, that is from address 0 to address 2 to the power k minus 1. Okay, that means that by using a, if your address bus contains 24 lines, okay, or if you are using 24 bits to address the memory, or if you are using 24 bits to address the memory, then we can maximum address this many locations, 2 to the power 24 locations, which is nothing but 16 megabytes, which is nothing but 16 MB of memory can be addressed, where 1 MB is equal to 2 to the power 20. Okay, if you have 32 bits to address the memory, if you have 32 bits to address the memory, that is, if the address line contains if the number of address lines are 32, if the number of lines in the address bus are 32, that means you have 32 bit to address the memory. Then using a 32 bit you can address this many locations, 2 power 32 locations, that is 4 GB of memory, where 1 GB is equal to 2 to the power 30. Okay, so one kilobyte is nothing but 2 to the power 10. 1 megabyte is nothing but 2 to the power 20. 1 gigabyte is nothing but 2 to the power 30, and 1 terabyte is nothing but 2 to the power 40. Okay, so the point here is, if we have n bits to address the memory, then using that we can address 2 to the power n locations, that is from 0 to 2 to the power n minus 1 locations. That's it. So that is the key takeaway here. Okay, fine. Okay, so even though the memory is a memory, even though the basic unit of memory is bits, so we discussed that memory is nothing but a collection of bits. So the memory is nothing but a collection of millions of bits. Okay, but even though the basic unit of memory is bits, uh, but it is not practical to address individual bits. It is not practical to assign addresses to individual bits. Okay, so normally we don't address memory at bit level. Normally we don't address memory at bit level, but what we do is, generally we address memory at byte level. Generally we address memory as byte level. That is, a byte is nothing but a collection of 8 bits. Okay, so so a set of 8 bits will give one address: 1 2 3 4. Set of 8 bits. So this is 8 bits: 1 2 3 4 5 6 7 8. For this set of 8 bits, we'll give some address. Say the address is 0 0 0. If you have, how many bits you are using to refer the address, that many zeros will be there. Okay, if you have 5 bits, then 5 zeros. Okay, then the next location, the next set of uh, 8 bits, that is the next byte, will be addressed as 0 0 0 0 0 1. Okay, so this is the zeroth byte. This is the first byte. Okay, and the next will be second byte. Next will be third byte. Like that we address. That is the general way to address the memory is as byte address. Generally, we don't address in terms of bits. Okay, if you address in terms of bits, there will be millions of billions of locations. Then the uh, managing the memory or performing some calculation will become more complicated. Okay, so that's the reason generally we address memory in terms of byte. Okay, so so the byte locations, as we already discussed, each byte in the memory will be numbered like this: 0th byte, first byte, second byte, and so on and so forth. Okay, right? So generally memory is addressed as byte. Okay, if the word length of a computer is 32 bit, if the word length of the computer is 32 bit, then each word will occupy 4 bytes. Okay, so let us say this is word and this is byte. Okay, and memory is addressed as byte. So 0th word will occupy from 0th byte to 3rd byte. Okay, because each word, the word length is 32 bits, that is 4 bytes. Okay, each byte is 8 bits, that is 4 bytes, so 8 fours are 32. So 0th word will occupy from 0th byte to 3rd byte. Okay, 0th byte, first byte, second byte, and 3rd byte, right? And first word will occupy and first word will occupy from fourth byte to seventh byte, 4, 5, 6, and 7. And second byte will occupy from 8th byte to 11th byte, 8, 9, 10, 11. Okay. And third byte will occupy from uh, third word, sorry, this is word. Okay, first word will occupy from 0th byte to third byte, sorry. First word will occupy from 0th byte to third byte. Sorry, 0th word will occupy from 0th byte to third byte. First word will occupy from 4th byte to 7th byte. Second word will occupy from 8th byte to 11th byte. Third word will occupy from 12th byte to 15th byte. Okay, so on and so forth. Right. Fourth word will occupy from 16th word to 19th word. Okay, so like that it proceeds. Okay, so if the this is the case if the word size is 32 bits. Okay, right, like that you can calculate for different word size. If the word size is 2 bytes, that is only 16 bits, then the first word will occupy only from 0 to 1, 0th byte and first byte. Second word will occupy from 2 to 3, that is second byte and third byte it will take. So first word. Second word will occupy from fourth byte to fifth byte. Okay. Third word will occupy from sixth byte to seventh byte. Fourth word will occupy from eighth byte to ninth byte. Okay. So depending on the size of the word, the each word will occupy that number of bytes, right? Okay. So, so that is what we have discussed. If the word size is 32 bits, then the successive words will be addressed at 0th, 4th, and 8th. Like, okay. So, I mean, first word starting address will be 0th byte. Okay. From 0th byte, it will use from 0th byte to 3rd byte. Okay. Or the 0th word starting address will be 0th byte. First word's starting address will be 4th byte. Second word's starting address will be 8th byte. Third word's starting address will be 12th byte, and so on and so forth. Fine. Before coming to big endian and little endian, let us discuss something else. So as we have discussed, the memory is addressed basically in terms of bytes. That is, the memory is byte addressed. Okay, and also we have discussed that the size of the word varies with computers to computers. It may be either 16-bit or 32-bit or 64-bit. It depends. There is a concept called word alignment. There is a concept called word alignment. What does it mean? It means that typically the size of the word will be a multiple of the number of bytes. Generally, the size of the word will be a multiple of number of bytes. Okay, so if the size of the word is is equal to the multiple of certain number of bytes, then that is called as a aligned word. Okay, so generally that is the case. Okay, if the size of the word is equal to the multiple of a certain number of bytes, then we call it as an aligned word. Okay, for example, if the word size is 16 bits, then what does it mean? It is nothing but 2 bytes. So it's a multiple of byte. If the word size is 32 bits, then what does it mean? It is nothing but 4 bytes. It is also a multiple of bytes. If the word size is 64 bits, then this is 8 bytes. So this is also a multiple of byte. Okay, generally in any computer, if you see, the word size will be some multiple of certain number of bytes. Okay, but there is no fundamental reason why it should be like that. Okay, there is no fundamental reason why it should be like that. So instead of 16 bytes, a word size can also be, instead of 16 bits, a word size also can be 18 bits. Instead of 32 bits, it can be 36 bit. Okay, which is not a multiple of a byte. Instead of 64 bit, it can be 69 bits. Okay, there is no reason why it should not be that way. There is no fundamental reason. Okay, but generally, typically computers follow this particular approach. That is, the size of a word will be a multiple of certain number of bytes. Okay, if the size of the word is multiple of certain number of bytes, then that is called as a aligned word. Okay. If the size of the word is not a multiple of certain number of bytes, then that is called as unaligned word. So these are examples of unaligned word. If the word size is 18 bits or 36 bits or 69 bits, then these are called as unaligned words. Okay. So this is the difference between an aligned word and an unaligned word. So this is something what we have already discussed. If the word size is 16-bit, then each word will be addressed like this. The first word will be addressed at zeroth. I mean the zeroth word will be addressed at zeroth byte. The first word will be addressed at first byte. Sorry, second byte. The first word will be addressed at second byte because zeroth word occupies zeroth byte and first byte. And the first word will be addressed at second byte and it will occupy second and third byte. And the second word will be addressed at fourth byte, that is it will occupy fourth and fifth byte. And the third word will be addressed at sixth byte and that will occupy sixth and seventh byte. If the word size is 32-bit, then the zeroth word will be addressed at zeroth byte and the first word will be addressed at fourth byte because now zeroth word occupies from zeroth byte to third byte. And the second word will be addressed from 8th byte because the first word occupies from 4th byte to 7th byte. If the word size is 64-bit, then the first word will be, zeroth word will be addressed at zeroth byte and the first word will be addressed at 8th byte because zeroth word is addressed from 0th byte to 7th byte. And the second word will be addressed at 16th byte because first word is addressed from 8th to 17th. Okay. So this is how the word address happens, right? Okay. Fine. Now let us come back to this big endian and little endian uh, assignments of uh, of a particular word. Okay, of a particular word. So what is generally in computers we follow little endian. Generally, in a typical computers we follow little endian format. Little endian format means uh, the the least significant bit or the least significant byte or bit, whatever it may be, that will be stored at the rightmost location. Okay, that will be stored at the rightmost location and the most significant bit will be stored at the leftmost location. So such a entry is called as little endian because this is ending with little. Okay, that is the value whose place position is least, it is ending with that, so it is called as little endian. Okay, right. So if you say, for example, I want to say 9. Okay, 9, what's the binary value of 9? So in 8421 code it is 1001. Okay, we say like this. So here this is a little endian format. Why? Because here what is the one's position value? It is 1 into 2 to the power 0. It is 1 into 2 to the power 0, which is nothing but what? 1. Okay, whereas this is 0 into 2 to the power 1. Okay, but it is 0, so it is 0. This is 0 into 2 to the power 2. As it is a multiple of 0, it is 0. Okay, this is 0 into 2 to the power 3. Okay, what is, sorry, this is 1 into 2 to the power 3. So what is 1 into 2 to the power 3? 2 to the power 3 is 8. So this is 8. So when you add all these things, you will get 9. Okay, so this is how it is stored in a typical uh, little endian computer. Okay, so this least significant value will go here and the other values will just follow in that order. Okay, that is from in the right to left and the most significant value will go here. Okay, right. But so this is the little endian format. But if it is a big endian format, if it is a big endian format, it is just a reverse of that. In a big endian format, what will happen in the sense, the most significant value will be in the right end. Okay, that is it will end with the most significant value and the least significant bit will come in the left end. Okay, so this is what a little endian and big endian is. You can generally assume a typical computer follows little endian format, But at some rare cases, some computers may also follow big endian format, and that is why we are discussing this topic. Okay. So here we are discussing little endian and big endian in terms of byte addressing, not in terms of bit. So again, let us assume that one word size is 4 bytes. Okay, one word. Let us assume one word size is equal to 4 bytes. That is 32 bits. That is 32 bits. Okay. So each word contains 4 bytes or 32 bits. Okay. So this entire thing is nothing but the length of this is nothing but 32 bits or 4 bytes. This is 32 bits. Bits I will represent as small b, or which is equal to 4 bytes. Okay. Now assume that you have some large number of words. Okay. You want to store in the memory. Okay. Then how will you store? How will you store? So the least significant value, the least significant byte will come in the, if you are using little endian format, this is a little endian format. When you are using little endian format, okay, say you have many words, word 1, word 2, okay, word 3, like that you have 100 words, okay, word 100, okay. So each word contains 4 bytes. Each word contains 4 bytes. Okay. So in that 4 byte, some the generally the leftmost is the big endian word and the rightmost is the little endian word. Okay. So when you use little endian format, the rightmost the zeroth word you will keep here. Okay. And the first word, sorry, zeroth byte, each word contains 4 bytes. So 0th byte will come here, first byte will come here, second byte will come here, third byte will come here. Okay, this is 0th word. This is word 0. So let us number this from word 0 to word 99 instead of 100. Okay, so 0th word, sorry. So, so it is word 0 to word 99. So the So zeroth, so for zeroth word there are 4 bytes. Okay, maybe it will be for zeroth word we can say it is byte 4, byte 2, sorry, byte 3, byte 2, byte 1, and byte 0. So that byte 0 will come in the little endian position. Then byte 1. I mean the byte 0 will come in the least significant position. Then byte 1, the next least significant. Then byte 2, the next least significant position, and byte 3 will be in the most significant position. Okay. Similarly, the next word, word 1, word 1. So word 1 will occupy from 4th byte to 7th byte, right? So 4th byte will come here, then 5th byte, then 6th byte, then 7th byte. So this ordering is from little endian to big endian, least significant position to most significant position. Like that it will go. So this type of ordering is called as little endian. Little endian. Okay. So the last word, that is 2 to the power k minus 4 word will be byte will be here, 2 to the power k minus 3 byte will be here, 2 to the power k minus 2 byte will be here, 2 to the power k minus 1 byte will be here. Okay. So this is the word address. The address of the 0th word start at 0th byte. The address of the first word starts at 4th byte. Okay. The address of the second word will start at 8th byte. The address of the third word will start at 12th byte. Okay. The address of the fourth word will start at 16th byte, like that. Okay. The address of the what do you call, the address of the last word will start at 2 to the power k minus 4th location. Okay. Fine. So this is the case for little endian addressing. But if the same thing, if you want to store using big endian, then also word 0, if you take word 0, it contains 4 bytes. What are they? B4, B3, that is byte 4, byte 3, sorry, byte 3, byte 2, byte 1, and byte 0. Okay. byte 3, byte 2, byte 1 and byte 0. There is no byte 4. Byte 3, byte 2, byte 1 and byte 0. Okay. When you use little endian, the byte 0 will come to the least significant port and byte 3 will go to the most significant port. But when you use big endian, byte 3 will come here, because now here this is the MSB. Okay, now here this is your MSB, whereas this is your LSB. Okay, so it ends with MSB. It is not ends with LSB. So that is called as big endian. So that the byte corresponding to B3 will come here. The byte corresponding to B2 will come here. The byte corresponding to B1 will come here. The byte corresponding to B0 will come here. Okay. Similarly, for the next word, the byte corresponding to B7 will come here. B6 will be here. B5 will be here. B4 will be here. So on and so forth. Right? So this type of assignment, memory assignment, is called as little endian or big endian. But in most often we use little endian, right? Then we will be discussing the various memory operations. Typically, there are two types of memory operations. These are load and store. So so normally when you fetch any instructions or data, we may generally, if you see the processor, either it want to fetch instructions and data from the memory, or it want to store instruction or data to the memory. Okay, if the processor want to fetch something from the memory, then it will use load instruction. Okay, if the processor want to store something into the memory, if the processor want to write something to the memory, then it will use store instruction. Okay, so the load instruction, what it will do, it is used to read or fetch contents from the memory. So it will just copy the content. Whatever the content that is previously in the memory, that won't be erased or it won't be updated. Okay, it will just copy it, right? The operation performed is called as load, right? And some address will be specified through this load operation. So the load operation will say that from which address the data should be loaded. Okay, say for example, I'm using LA. So LA represents load. Okay, so I'm saying that LA, say for example, LA something, say sorry, say LA, LA K comma yes. Okay, let us assume this K and S are registers. Okay, then what does it mean? A K, say K is some address. Let us assume K is address. So then whatever the content available in K, okay, K is address. The content available in the K should be loaded into S. That is what this instruction says. If K is an address, okay. So this load instruction will often include some address, from which address the data should be loaded. Okay, and the resultant data will be loaded into some registers. Okay, so instead of yes, it may be R0. If R0 is a register, then the content pointed by this address K will be loaded into the register R0. Okay, right? The content pointed by the address K will be loaded into the register R0, right? So this is what a load instruction will do. It will give an address and the data available in that address will be loaded into appropriate register. Similarly, when you say store, the store operation will be used by the processor to write something to the memory. Okay, so when you perform the write operation into the memory, if that particular location already contains some data, that data will be overwritten. Okay, so that data will be overwritten with this new data. Whereas when you perform load operation, the memory content will not change. Just a copy of that content will be moved to the appropriate register. Right? For store also, you should give some address. Some address should be given. At which address it should be stored, and you have to pass the data. Generally through registers, the data will be passed. So this data will be stored at so and so address. For example, if you give STA, that is store some information at this particular address. Store, say again I'm using this store stak comma r1 r1, which means again this k refers address. So at this particular address, k refers some address. Okay, so memory contains many locations. Say this location is k. So in this location k, the content of r1 should be written. If r1 contains 100, okay, then 100 will be written here. If previously this location k contains 99, then that 99 will be now overwritten by this content 100. Okay? So this is what the load and store does. So load is used to load something, retrieve something from the memory, and store is used to write something to the memory. Load will not change the memory content, but the store will change the memory content. And load is used to, when you use a load instruction, you should pass the address and also where the data should be read, the register, the name of the register. Similarly, for store also you should pass the address, and also you should give the data that is to be returned to that particular memory. Okay, so fine, let us stop here. Thank you.